Okay, last lesson we introduced exponential functions, which, if you recall, are whenever you have a variable that is an exponent. Today we're introducing logarithms and logarithmic functions, which are the inverse of those exponential functions. So we're going to go ahead and take a look at what these logarithmic functions look like and how to solve them and use them. So first off, here's just an example of what a logarithmic function looks like. So the red line there is the exponential function that we graphed yesterday. That bluish purple line is the logarithmic function. So you can see it's a reflection over this, and then this line here is the xy line that shows what that's being reflected over. So this is our logarithmic function, and this is the exponential function. Just to give you an idea there. So now let's take a look at what it looks like. So we say logarithm with base b. So let b and x be positive numbers. The logarithm of x with base b is denoted by log, and you say that log base b of x. And is defined as the exponent y that makes the equation b to the y power equal x true. So really what you're doing is you're isolating the exponent. You're saying y is the exponent, and log base b of x, you rewrite that as b to the y power equals x. So we're rearranging it a little bit when we take the log and finding out what that means and what that equals. So if you don't know, like yesterday, you were solving for some of those exponents in the variable, or excuse me, the variables and the exponents. This time, if you can't find those directly like that, you're looking at setting up a logarithm so that you can try to find those. Alright, example number 1. All they want us to do is rewrite these in exponential form. So looking at these, to write them in exponential form, the base stays your base. So that's going to be our big number. So we have 8 to the 0, this is your exponent, to the 0 power is equal to 1. And that's exponential form. So over here we have 2 to the negative 4th power is equal to 1 over 16. Because remember, that means to take the reciprocal, so it doesn't make it negative, it just makes it a fraction. Now we're going to go the other direction. Let's write these in logarithmic form. So for this one, we're going to say 10 to the 3rd power is equal to 1,000. So you would have log, the base stays the base, so log base 10 of 1,000 equals your exponent, which is 3. So the exponent is always the thing that's isolated by itself. So over here we have log base 9 of 3 is equal to 1/2. Or excuse me, yes, to 1/2. Now when it says to evaluate, for now we're going to use exponential form to evaluate these. Eventually we'll get to the point where we can evaluate them without that. But looking at log base 2 of 64. What I'm going to do is set that equal to an unknown exponent. So I can rewrite this as 2 to the x power is equal to 64. Well, now we know how to do this because we did it in yesterday's lesson. So we can do 2 to the x power is equal to 2 to the... Now we want to figure out 64 is 2 to what exponent? It's actually going to be to the 6th power. So then we know x is equal to 6. And since x is equal to 6, that means this logarithm is equal to 6. So that is your answer. So a similar thing with log base 3 of 81. We're going to set that equal to some variable, so log base 3 of 81 is equal to y. So then 3 to the y power is equal to 81. Yesterday we talked about a couple of times, 81 is 3 to the 4th power. So once your bases are the same, then you can just say y is equal to 4. Alright, and here are some characteristics of logarithmic functions that you need to copy down and know and recognize so that as you're solving these, you can make sense of, okay, what I'm getting makes sense, or what I'm getting doesn't quite fit, so I must have done something wrong. So, characteristics. A logarithmic function, remember, is just where it's actually going to be a function. So it's continuous and one-to-one, so we talked about that with exponentials. The domain is all positive real numbers. The y-axis is an asymptote instead of the x-axis. The range is a set of all real numbers. And the graph contains the point 1, 0. That is, the x-intercept is always going to be 1, unless you add or subtract to it a little bit. Alright, so now we're solving ones where we know the exponent, and we're trying to find out what does that equal. So again, the easiest way to do this would be to rewrite that in exponential form. So we have 4 to the 5/2 power is equal to n. So now all we have to do is evaluate this. Remember, fractional exponents means you have a root. So that means you're taking the square root of 4 and then raising that to the 5th power. The square root of 4 is 2. 2 to the 5th power is going to be 32. So then you would say log base 4 of 32 is 5/2. Same thing over here. We're going to have 16 to the 5/2 power is equal to something else. So then we have the square root of 16, then raise that to the 5th power. So we say 4 to the 5th power, and that is going to equal 1024. So a lot of these can all be solved by rewriting them for right now in exponential form. Alright, so now we're going to change it up a little bit and do some inequalities. So a lot of this is going to be pretty similar to what we did with exponentials and when we do it with just an equal sign. However, we are going to change things up just a little bit, and it's going to give us a broader range of things instead of just having one value. So it's going to be kind of your typical change with exponentials, or with inequalities, excuse me. Okay, so looking at log base 5 of x is less than 2. The one thing you want to realize is that a logarithm, the value inside of here, if you'll notice, if you remember the x values, the domain is all positive real numbers. So when you put this in here, so first we're going to write this in exponential form. So 5 squared, and the exponent stays on this side of it. So it's going to be 5 squared is greater than x. Just remember, base 5 squared equals x. So it's greater than. However, inside of there, we can never be 0 or negative. So automatically, you're always going to put that as greater than 0. So then our solution here would be that x has to be somewhere between 0 and 25 is the final answer there. And if we looked at that, we could say, okay, is that going to work for anything? And you could test different values and you could see that it is going to work. So the important part of that there, and that changed a little bit there, is looking at the fact that we have to be bigger than 0 inside the logarithm. So then that's going to be anywhere in between 0 and 25. So taking a look at that next one, log base 4 of x is greater than 3. So this time they've reversed it around. So we want to see, so we're going to say 4 to the third power has to be less than x. Now, being that this is a positive number, we don't have to worry about it being greater than 0, because if it's greater than this, it's already greater than 0. So then 4 to the third power, we're saying x has to be somewhere that's greater than 64, which is bigger than 0. So technically you would say all this has to be greater than 0, which 64 is always greater than 0, so that's automatically satisfied. So we're not really worried about that. It's just x is greater than 64. So whichever side the exponent is on, so the 2 was the exponent and the 3 was the exponent, that stays on. When you rewrite the base really kind of transfers itself to that side of it. So it is greater than 3, so that meant 4 to the third was on the bottom end of that of the inequality. Alright, your homework then is page 515, 23 to 45 odds. And so a lot of that's going to be rewriting in exponential form, using some of these properties we discussed, as well as other things. Alright, I'm going to continue right on. Let me change that date. So I am going to continue on. The homework I divided up so it's not so overbearing. I am going to do this over a couple of days because this is stuff I really want you guys to know. However, I'm just going to have you continue to watch the video and to do all of this in one day, and that way you can do all of the homework in one day, or we can you can split that up as you see fit. So we're going to go ahead and jump right back into 9.2. In the property of equality for logarithmic functions. What that's saying is, if you have, this is very similar to what we do with exponentials, where if the base was the same, you could just eliminate the whole base and just set the exponents equal to one another. Same thing here. If the base is the same, so that log base b, if that's the same, then you can just say the x and the y are equal to one another. So it's a very, very similar property. So for instance, for both of these, I have log base 5 and log base 5. Now you have to make sure that you only have one logarithm on one side and one logarithm on the other side, and they have to match bases. If that's the case, essentially what happens is I drop those and I just say p squared minus 2 is equal to p. Now why does that work? If I jump over here and just rewrite log base 5 of p squared minus 2. Remember, this is equal to some exponent. Okay, we don't know what that is. It's some exponent. So 5 to the x power is equal to b squared minus 2. Well, then what we're saying is that same exponent is equal to log base 5 of p. So then I say now 5 to the x power is equal to p. So then I drop those and I can say, okay, p is equal to the other thing. So that's kind of why that works that way. It's a quadratic. I'm going to isolate it and set it equal to 0. Factor. So p minus 2 equals 0, so p is equal to 2. And p plus 1 equals 0, which means p is equal to a negative 1. We have to check our solutions. There's almost always going to be, again, one of those ones that doesn't work. Because if we look back, what has to be true about the number inside the logarithm? It has to be positive. If I put a 2 in there, that's fine. If I put a negative 1 in there, it's going to be undefined. We cannot use the p equals negative 1 because it's going to make this entire logarithm undefined. As well as this one, because the negative 1 squared is 1, minus 2 is a negative 1. So even though they're both log base 5 of negative 1, so you're saying they're the same thing on both sides, you cannot have the negative inside the logarithm. Very similar thing that we talked about before with inequality, or equality, we're now going to talk about with inequality. Where if you have one logarithm that has the same base as another is greater than, then you can just drop those and say that x is greater than y. Same thing, or x is less than y. So it's a very similar thing, we just have less than or greater than instead of equal to. So if we look at this example, again, one logarithm, same base, one logarithm, same base. So it's just 3x minus 4 is less than x plus 6. When you solve it, we subtract x, so we get 2x minus 4 is less than 6. Add 4, 2x is less than 10, so x is less than 5. But we have to make sure that it stays greater than 0. So that's the other piece you want to make sure of. You have to make sure that both of these things stay above 0. So what you're going to do off to the side then is you're going to say 3x minus 4 has to be greater than 0. So x has to be greater than 4/3. But then also on the other side, we're saying x plus 6 has to be greater than 0. So x has to be greater than negative 6. Well, this is higher than negative 6, and both things have to be satisfied. So x is not only less than 5, it has to be greater than 4/3. So you have to take both of those things into account and give yourself two bounds. One at the top and one at the bottom. And that finishes out section 2. So now you'll be able to do both homework assignments, the one that was after the first part of that, and the continuation of that one from the second half of that lesson.